All right there. Hi guys. My name is Wilfrid. I'm a senior math tutor, and I'll be covering 8 questions today from calculus and also a bit of vectors, I think. Oh, sorry, no, a bit of integrals. A little backstory about myself. I graduated from my master with a major in biochemistry and a minor in mathematics. And if you have any other questions regarding your mathematics problems or calculus problems, please submit them through OneClass. Okay, so let's just begin with the first question. So the first question reads, find the partial derivatives of the function z equals x. Oops, where'd my question go? Find the partial derivatives of the function z equals x sine x of y. So when it says partial derivatives, you guys can notice here that our function here is actually consisting of 2 variables, right? We have what's going on? Why is my computer like this? Okay, so we have a function here, function z, which equals x times sine of xy. Okay, so you can see here that our function z is a function of 2 variables instead of 1. So deriving in terms of 1 variable is what we call a partial derivative in this sense. So we keep the other variable as a constant and we derive for the other variable. And what that does, it tells us the rate of change of that variable when the other variable is constant. So how you partially derive is you can write what we say dz of dx. So you notify to the reader that you're deriving in terms of x. And you're keeping y constant, okay? And all the other derivative rules applies. The power rule applies. The product rule applies. The quotient rule applies. Everything else applies, except the fact that you keep the y variable constant, okay? So let's first of all do the partial derivative in terms of x, okay? So here we can see here that we have a product rule because we have x times sine of xy. So we're going to derive the first function x and keep the second function constant or the same, and then we're going to do a plus sign, and we're going to derive the second function and leave the first function the same, okay? So this is what we're going to get. So if the first function is, we're going to leave the first function underived, I guess you can say, and we're going to derive the second function. Okay, so d of dx of sine xy. Okay, so we're going to derive the second function, and then we're going to sum them to the derivative of the first function, so d of dx of x times sine xy. Okay. So what we get here is x times, so the derivative of sine is cos, so cos xy, plus the derivative of x by itself is 1, so 1 times sine xy. So that's the partial derivative of our function z in terms of x, okay? So you see here that we ignored y entirely and left it as a constant. And our partial derivative of y will be more clear what we mean by constant, okay? So let's do the partial derivative in terms of y now, okay? All right, so this time we have a chain rule, right? We have a function within a function, okay? So our chain rule suggests that we derive in terms, we set a function to be equal to u, and then we derive in terms of that. Okay, so let's say that u equals x times y, okay? So we have dz of du. So I'll just write a note here. Let u equal x times y, okay? So if u equals x times y, we have dz of du of sine x sine u, x times sine of u, and then we multiply that to du of dy of xy. Okay, cool. All right, so the first outside derivative would be, so the derivative of sine is cos, and we leave x to be a constant. So we assume that's like a number, right? So with any other constant, we just keep it the same. So this would be 4 cos u. And derivative of xy would just be x. So, oh, wait, why do I write 4? It should just be x. This x, this should be x. Okay, cool. So we're just going to sub back in our u here now. So we have x squared cos of xy. Okay. So you see here that we kept this x here and this x here constant, right? We didn't change anything. We didn't get rid of it, but we treated it as a constant. So this is how we do the partial derivatives of x and y. And this works for any multivariable function. And as we go deeper, you can also, for the second derivatives, you can do a mixed derivative. You can do two partial derivatives of the same variable. You can do a lot of things. So, okay, so the junior tutor also did the solution. They partially derived in terms of x. They used the product rule, the power rule, and for the partial derivative of y, they used the chain rule with also some trigonometric identities and trigonometric derivatives. So this solution is correct. Cool. Okay, so moving on to question number 2. So what is the integral of x squared minus 4 from the interval 0 to 4? So in this case, what they're asking us to solve is the definite integral of the function x squared minus 4 from interval 4 to 0. Okay, that's what they're looking for. And they're looking for the area under the curve, basically. So to do these definite integrals, first of all, you'll have to integrate your inside function, and then you have to calculate the area with the designated interval. So the junior tutor outlined some of the formulas or some of the properties that we can use here. They've listed out the difference rule of integration, which suggests that the integral of two functions that are subtracted from each other can be split up. It's kind of like a distributive property. They also suggested that we use the power rule of integration, which pertains to how to integrate variables with exponents and powers. And finally, they suggested that we use the constant multiple rule of integration, which tells us how to integrate constants. Okay, so we're going to use those rules. So the first thing that we're going to do here is that we see that our function here could be considered the difference between two functions. So we're going to use a difference rule of integration to break them up. Okay. So this would be x squared dx minus 4 dx. Okay. So our first integral here, we can use the power rule, which suggests that x to the n equals, integral of that is x to the n plus 1 divided by n plus 1. So we're going to do that here. So after we do that, this function is done is done for the integral. So this would be 1 over 3 times x cubed. And the interval here is 4 and 0. And we're also going to use a constant multiple rule of integration for this one. So that would be 4x. Okay. 4, 0. Okay, cool. So you guys can notice here that in our suggested rule properties, they included the c constant, right? So you only consider adding the c constant when you have an indefinite integral, okay? Because when you're calculating the area for indefinite integrals, you actually cancel out the constant when you're calculating your integrals, okay? Cool. So now we're going to calculate the area under the curve, or we're going to calculate the difference between the interval 4 and 0 of these two integrals, I guess you can say. So let's do that now. So we have 4 to the 3 is 64 over 3, right? 4 cubed is 4 squared is 16. 16 times 4 is 64 minus 1 over 3. Okay, so that's our first one. This should be a 0. Why did I? So this should be 0. Sorry, that was a 1. So this should be a 0. Okay. The second function is 16 minus 0, okay, which is a 16. So all we got here is 64 over 3 minus 16. Okay, cool. So now we're going to simplify this fraction here. This is 64 minus 48 divided by 3, and that is equal to 16 over 3. So therefore, the definite integral from 4 to 0 of x squared minus 4 is equal to 16 over 3. Right? So that's the area under the curve of x squared minus 4. Okay. So the junior tutor also did the same solution. They used all these properties to simplify their integral, and then they integrated, and then they calculated the area under the curve, or the difference between 4 to 0. Yeah, and they came up with the same solution. Okay, cool. All right, moving on. So the third question is, what is the derivative of y equals cos x squared? Okay, so the first question I kind of covered chain rule a little bit, but this question really focuses on chain rule and how you use it. Okay, so let me illustrate what chain rule is again. So whenever you see a function within a function, you can apply the chain rule, which means that you derive the outside function and you multiply that by the derivative of the inside function, right? So the convention of writing it, so let's say that you have dy over dx, and you have a function within a function. You can equate this to dy over du. So you integrate the whole function in terms of u, and then you integrate u in terms of x, or you derive u in terms of x. Okay? So if you were to have a function within a function, you can split it up and you can equate it to the derivative of the function in terms of u, and times the derivative of u in terms of x. Okay? So using the chain rule means that you'll have to use a substitution variable to set to u. Okay? So here, we're going to let me write out the derivative first. Okay, so we're looking for dy of dx. So we're looking for d of dx of cos x squared. Okay. So first of all, why don't we let u to be x squared? Okay. Let u equal x squared. Okay. So if that was the case, then we have d of dx of cos u. Okay. So now we're going to use our chain rule, which suggests that we do dy over du. So we do d over du of cos u. And then we multiply that by d of dx of x squared. Okay? Cool. So according to our trigonometric derivatives, the derivative of cos is negative sine. So we just write negative sine u here. We'll put some brackets around this too. And the derivative of x squared using our power rule is 2x. Okay. So now all we need to do is just sub back in our u here. So this will be negative sine x squared times 2x, or negative 2x sine Alright, so the junior tutor, what happened here? So the junior tutor got this question wrong actually. They probably just forgot to write this as sine, but they derived cos into sine, and then they reverted it back to cos for some reason. And then they said it was cos. So this correct. Cos of u sine. Yeah, so yeah, they reverted it back for some reason. I don't know why. That's fine. So the solution is incorrect. All right, so question number 4. How to prove sine of 2x equals 2 times sine x cos x using other trigonometric identities, okay? So this is one of those classic proof questions to prove trigonometric identities. So this is a double angle proof, and they're asking us to use previous trigonometric identities to prove this. So we have to remember that this is a very important trigonometric identity, that the sine of x plus y, so the sine of two angles added together, can also be is equated to the sine of x, sine of cos y, plus cos of x times sine y. Okay. If you want the proof to this one, you will have to search it up. And we can also cleverly write sine of 2x to be sine of 2x can also be written as sine of x plus x. Okay? With these two different, I guess, properties in mind, we can now prove this trigonometric identity, okay? So let's do the left-hand side, okay? So left-hand side is sine of 2x. You can write that as sine of x plus x. And using our previous known trigonometric identity, you can write this as sine of x times cos of x plus cos of x times sine of x. And this equals to 2 sine of x cos x, which equals the right-hand side. So we just proved this trigonometric identity. That was pretty simple. In your questions and homework, there will probably be very unfamiliar trigonometric equations that you have to prove using the full roster of trigonometric identities. And it really only takes practice to really try to understand what kind of tricks and techniques that you need to use and which kind of identities you need to use for certain questions. So this solution is correct. Cool. Okay, moving along. Now we're going to talk about implicit differentiation. So usually, implicit differentiation requires us to have a function y be in terms of a independent variable x. So we could technically explicitly derive this equation by isolating for y, right? So we'll have to do, so let's write out the original equation first. So this would be x squared minus y squared equals 25, right? So we could explicitly derive this. Explicit differentiation. We can explicitly differentiate this by isolating for y, right? So we can say we move everything to the left except for y. So we'll have 25 minus x squared. So we'll have x squared minus 25. Okay, and then we square root everything. And we could explicitly derive like this, right? So we can say, okay, so we're going to do a dy of dx here. So implicit differentiation does not require us to isolate for y squared. And it's very useful for functions that we cannot explicitly derive, or we cannot find the function y in terms of x only. So implicit differentiation suggests that we just derive as is, and we derive everything in terms of x, okay? So implicit differentiation. It suggests that we just derive, sorry, that was, it suggests that we just derive in terms of like this. So we do d of dx of x squared minus y squared, and we do d of dx of 25, okay? So if we were to explicitly derive this, this is what we'll get, okay? So this is our difference quotient, or differentiation, so we can split it up. So this would be d of dx x squared minus d of dx y squared, and this just equals 0, okay? All right, so derivative of x squared is just 2x, and derivative of this would be a chain rule, right? So there's an outside function and there's an inside function, right? So the outside function is going to be 2y, and our inside function, we don't know what the derivative is in terms of x solely, so all we're going to write is y prime, or dy of dx, okay? So we're just going to say derivative of y is just dy dx, we just don't know what it is, and this is equal to 0. We're going to isolate for dy dx now, okay? So dy dx equals 2x divided by negative 2y, okay? And we get x over y as our final answer, okay? So you notice here that our derivative in the end is in terms of both variables here, okay? So you can see here that we have x and y. Compared to explicit differentiation, if we were to derive this, right, we would have a chain rule here, so it'll be 1 over 2 x squared minus 25 negative half, and then derivative of the inside is just 2x, which would equal to x divided by the square roots of x squared minus 25, okay? So that is our explicit differentiation, and we see here that our function here is in terms of only x, okay? So we have derived in two different ways, but our derivative of dy dx is in terms of x and y through implicit differentiation, and our explicit differentiation is only in terms of x. In this case, since our function is actually easily isolated for y, we can sub back in y here, right? So if we were to say sub in y, we can get dy over dx equals x divided by, y is here, right? Y equals root of x squared minus 25, root of x squared minus 25, and we get the same thing. So we know that we implicitly differentiated correctly. Now, this was a very simple, I guess, example of implicit differentiation, and you can also do it explicitly, right? But there are some functions out there that you cannot explicitly differentiate easily. So implicit differentiation is actually the preferred method of finding the derivative, okay? So the junior tutor, they implicitly derived. They suggested that we use the power rule, and then they used the power rule and the chain rule here, and they came up with the same solution as we did. So this solution is correct. All right, cool. So we're going to talk about the squeeze theorem again. So the question reads, what is the limit of sine x over x as x goes to infinity? Okay. So the squeeze theorem goes like this, okay? So it's a squeeze theorem. Let's say that we're trying to find the limit as x approaches value a of a function, okay? And we cannot find that limit using conventional methods of substitution or algebraic techniques or using the conjugates. We can't find it conventionally. Well, the squeeze theorem suggests that we take our function f of x and we squeeze it. So we need to know that the range of f of x is less than or equal to, let's say, the range of h of x, okay? So we find another function that will always be greater or equal to f of x. And we find another function that will always be less than or equal to the range of f of x, okay? So once we have this inequality set, right, if the limit of g of x and h of x as x approaches a is the same, then f of x also has that limit, okay? So if the limit of g of x as x approaches a and the limit of h of x as x approaches a both equal the same limit, then the limit of f of x as x approaches a also equals L, okay? So this is the squeeze theory, all right? This is a squeeze theory, okay? So this is a very useful theorem. If you want a proof on how the squeeze theorem works, you can search it online, but it has something to do with the fact that we're constricting and maintaining the range of f of x between two very similar functions. And if those functions have the same limit, then any function within the middle or squeezed within the middle also will have the same limit. So not only talking about f of x, there could be other functions that are also maintained within this range of functions here, and they will also have the same limit. Any function within this range will have the same limit. And the very useful thing about the squeeze theorem is that you can make g of x and h of x very simple functions that you can calculate the limit of. And if the limit equals the same, then your very complicated function in the middle, that limit will be the same. So you can bypass all those tricky techniques of using algebraic or conjugates or some unknown or some obscure method of finding that limit. Okay, so in our example here, we have the limit of sine x over x as x approaches to infinity, okay? So as x approaches to infinity of sine x over x, we have a problem here already, right? So sine x is an oscillating function. That means that it always wiggles between 1 and -1. So if we were to plug in infinity, we actually don't know what the limit is because it could be going up towards 1, but once it goes up towards 1, it starts going back towards -1. And since it's oscillating, we don't really know the limit of sine of x in general. So this is just, we don't know what the limit is, right? So using our squeeze theory, right? So let's say, first of all, that sine of x, let's squeeze it between two different functions, okay? Oops. Let's squeeze it between g of x and h of x, okay? Let's say, let h of x equal -1, okay? So we're going to say, let's make h of x the most simple function, -1. It does not change, it's just constant. And g of x, let's make it equal to 1. All right, let's see if our inequality holds here, okay? So therefore, we'll have -1 less than or equal to sine of x and less than or equal to 1, okay? As you can see here, this is basically what sine is, right? It ranges between 1 and -1. It never goes greater than 1, never goes less than -1. So we have found a squeeze theorem, but this is not actually our function here, right? This is just sine of x, right? So why don't we divide our whole inequality by x, right? If we divide our whole inequality by x, we got negative 1 over x divided by sine x over x less than or equal to 1 over x. So now we have squeezed our actual function between two simpler reciprocal functions, right? And now, if we can calculate the limit as x approaches infinity of h of x and g of x, and they equal the same thing, then we know sine of x over x also equals the same thing, okay? So let's calculate the limit as x approaches infinity of negative 1 over x, okay? That would equal to, using substitution, that would equal negative 1 over infinity. Whoops. Negative 1 over infinity. And we know that anything divided by infinity is going to be 0, okay? How about the limit of x approaches infinity of 1 over x? That's the same thing. It'll be 1 over infinity, and we get 0. So those equal the same. So therefore, according to our squeeze theorem, sine x, the limit of sine x over x as x approaches infinity equals 0. So we had to do nothing to sine x over x. We just calculated the limits of these two simpler functions, and we found our limit of our middle function. So that's how you use squeeze theorem to calculate the limits of functions. It doesn't work for all functions. Sometimes you have x squared and you don't know how to contain the range of x squared. Actually, you really can't contain the range of x squared. But the squeeze theory is really useful for these kind of oscillating functions because they have a pertained range that is very easily interpretable and easily understood, right? So the junior tutor, when they set up their bounds for the squeeze theory, they said that sine x over x will always be less than or equal to, or always be greater or equal to 0. And I have a problem with this because I don't think this is the correct bounds for it. And if we were to do a graphing calculator of it, let's say if we do graph calculator, right? So if you were to graph sine x over x, you see here that it does actually, in fact, go below 0. So sine x over x actually never is actually sometimes less than 0. So these bounds actually don't work. So even though, they set up the squeeze theory or the bounds wrong, but the limit still maintains to be the same. But however, because of the bounds that are wrong, this solution is incorrect. Okay? So okay. All right, let's move on to the question number 7 here. Okay. So question number 7 reads, find the area of the region bounded by the graphs of the equation y equals x minus x squared plus 2x and y equals to 0. Okay. So this is a classical integral question, which asks us to find the area of the region bounded by two graphs. Okay. So to do this, of course, you have to calculate the integral of a function, but you have to figure out the bounds first. Okay. So it's always very helpful to graph our functions first, or our equations. In the future, however, if you're very confident, you can just find the points of intersection and you'll be good. But here we're going to graph it first. Okay, so let's say that is the x-axis and the y-axis. So our first function is just the x-axis, which is y equals to 0. And our second equation is the parabola negative x squared plus 2x, okay? So the zeros for this are 0 and 2. Okay, so we have something like this. Okay, and this equals to y equals negative x squared plus 2x. We know it's pointing downwards because the a coefficient is negative, and the zeros, I just looked at the graph here, but you can find the zeros by factoring this. So this is 0 and this is 2, okay? 0 and 2, and that's the vertex. Okay, so they're asking us to find the area of the region enclosed by these two graphs, which is this. So we need to find the integral of this. Okay, so the integral of this would be the area under the curve of y equals negative x squared plus 2x enclosed by the x-axis, okay? And the points that we're looking for here are the points of intersection between the x-axis and the parabola, which are 2 and 0. So those are our bounds. So basically, we're finding the area under the curve between x equals 0 and x equals 2. Okay, so we have found our integral, and we need to set that up now, right? So the area under the curve would equal to, so let's say area equals to the integral of the bounds 2 and 0 of the function negative x squared plus 2x d of x. Okay, so we need to find this integral. All right, so using the laws and the properties that we used last time in the question, we're going to integrate them using the difference rule, which suggests that we can break these up. Oh, this is not different. This is the addition. Sorry. 2x dx. We're going to use our power rule here, which is 2, 0, negative 1 over 3 x cubed. This should just be this. Plus, this is also the power rule, but since we have a 2 down here, it's very convenient for us. It's just x squared, 2 and 0. Okay, and now we're going to calculate the area of these two, which is negative 8 over 3 minus 0 plus 4, which equals to negative 8 plus 12 over 3, and we get 4 over 3, and that's the area under the curve, 4 over 3. Therefore, the area enclosed by negative x squared plus 2x and y equals 0 is 4 over 3. Okay? Cool. All right. So whenever you're calculating any kind of area enclosed by the curve, this is a very simple example, but sometimes you'll have a line and a parabola, sometimes you'll have a cubic function, sometimes you'll have two circles. Always try to find the point of intersection, and by finding that, you will find your bounds and what you need to integrate for. In this case, we found the point of intersection between this parabola and the x-axis, or it's just as zeros. We use those as bounds, and we calculate the definite integral across those two that interval. Okay, so this solution is correct. Okay. I should have one more question, but I guess I'll leave this question for next time, I guess. So that concludes today's session. Thank you guys so much for listening. If you have any other problems with your calculus homework or your tests or anything with integrals, please submit them through OneClass. And I hope you guys have a good day today. All right, I'll see you guys next time.